In our first looks at differential equations, the only way we had of solving differential equations was essentially to guess a solution and then check that our guess was correct. In most situations, that's not very practical because the chance of you guessing correctly is pretty small. So we really should come up with some way of computing solutions to differential equations rather than just guessing them. So here's an example. So let's see if we can solve the equation dy dx equals x times y. Now the reason this is so difficult to guess a solution to is because the way this equation is describing our unknown function y is just kind of complicated, since y and its derivative are sort of mixed together in this equation. So we're looking for some function whose derivative is equal to x times the original function. That's just kind of an awkward description of a function. So, one idea for how to handle this is, what makes this awkward is the way that x and y are all mixed together in this equation. So why don't we just try to separate them? We could try to get all of the x's on one side of the equation and all of the y's on the other side of the equation. So we could start by dividing both sides by y. This would give us something like 1 over y times dy dx equals x. And so now we have all of the y's on the left-hand side of the equation. It might look at first like we have all of the x's on the right-hand side, but actually, there's an x here in our dx. So often when we see dy dx, we think of this as a single entity, the derivative of y with respect to x. But remember, an alternative way of thinking about dy dx is that it's the ratio of differentials, dy and dx. So we can treat this dx as sort of an independent entity, or an entity independent from the derivative, and we could multiply both sides of this equation by dx. So on the left-hand side, the dx simplifies, so we get 1 over y dy equals x dx. Okay, so that's fine, but what do we do with this? Well, when I see a function of a variable and a differential like this with the same variable in it, I want to integrate. It just kind of seems like it's set up for integrating. So what we could do now is just integrate on both sides. And kind of a funny thing is happening. The variable that we're integrating with respect to on each side is different. On the left, this is an integral with respect to y, and on the right-hand side, this is an integral with respect to x. And, this happened because we separated the differentials like this. So on the left-hand side, the integral of 1 over y dy, that's natural log y. On the right-hand side, the integral of x dx, that's 1/2 x squared plus a constant. Right? We could have put this plus c on either side of the equation, but we have to have a constant of integration somewhere when we do indefinite integrals. Okay, now we need to finish solving for y. So, we need to unpack the y from this natural log, so let's exponentiate like this. So we get absolute value of y is equal to e to the 1/2 x squared plus a constant. Because there's a sum in this exponential here, I'm going to split this up. I'm going to write this as e to the c times e to the 1/2 x squared. This e to the c, this is really a constant. So I'm going to give this constant e to the c a name. I'm going to call that a. And because it's e to the c, it has to be greater than or equal to 0, or greater than 0, actually. Right? So we get absolute value of y is equal to a times e to the 1/2 x squared, and a has to be greater than 0. But if you look at this equation, we have something whose absolute value is an exponential times a positive constant. Well, there are two possibilities for y in here. Either this constant is positive or it was negative and we took its absolute value. So if we remove the absolute value, that has the effect of removing this restriction that a has to be positive. So now a can be anything that isn't 0. Right, it could be negative. All right, so we have a solution to our differential equation. We think. This is sort of a strange process. It's the first time we've done this, so let's actually check that this solution really is a solution. So remember, the original equation was dy dx equals x times y. Now, before we plug in this formula to check that it's a solution, remember we said that a shouldn't be 0, but if you plug 0 into this differential equation, it actually works. So the fact that we thought a couldn't be 0 was really just kind of an artifact of how we solved this differential equation. In fact, a can be 0, so we'll just cross out this restriction. A can actually be anything. Okay, so now let's check to see if this solution that we found really is a solution. So we need to find its derivative. So dy dx is a times, and then derivative of the exponential part, so e to the 1/2 x squared, times the derivative of the exponential, so that's 1/2 times 2x. So that's, let's see, a times e to the 1/2 x squared times x. And yes, that satisfies this differential equation because the derivative is the original function times x. So this solution that we found really is a solution to the differential equation. In fact, it's a general solution. So this isn't totally obvious, but in fact, every solution is of this form. All right, so let's have a look at another example of a differential equation. So how about dy dx equals sine x over cosine y? So I definitely would not be able to guess a function y that satisfies this differential equation. It just seems too complicated. But we can try the same idea. So let's separate the variables. So we can multiply both sides by cosine y, and also multiply both sides by dx. So that gives us cosine y dy equals sine x dx. And now this is set up to integrate on both sides. So then we get, let's see, sine y equals negative cosine x plus a constant. And then again, we need to solve this for the unknown function y. So we just take arcsine on both sides. So we get y equals inverse sine of minus cosine x plus a constant. Okay. And actually, this isn't a general solution yet, even though we have plus a constant here, because we didn't write down every solution to the equation up above, right? Remember, there are lots of symmetric and periodic solutions to this sort of trigonometric equation. So to get a general solution, we should write down every possible solution to this equation involving sine. So we need to add multiples of the period, so plus 2 pi k. And also we need to write down the symmetric solution for sine, which is, so inverse for sine, the symmetric solution is pi minus the original solution. So pi minus inverse sine minus cosine x plus c, and then of course plus multiples of the period, plus 2 pi k. All right. So the general idea here of separating the variables, integrating, and then solving the algebraic equation is still the same. It's just because of the fact that we have some trig functions, we get this little wrinkle involving periodic and symmetric solutions. So what is it that made this trick work? Well, if you look at both of these examples, what made the trick work was we were able to separate the variables, so separate x and y, just by doing some multiplying, right? It's the fact that we were able to multiply or divide to separate the variables that made it so that we had a function of y times dy, and then a function of x times dx. I shouldn't use the same letter because it's a different function, right? So it's really this structure that makes this whole thing work. So in general, if we have this kind of equation, so if dy dx is equal to some function of x times some function of y, this sort of equation is called a separable equation, and we can solve this sort of equation, this separable equation, by using this algebraic trick. So just multiply and divide to separate the variables, which, in its general form is going to turn our general separable equation into 1 over gy times dy equals f of x dx. And then you'll integrate. On the left-hand side, your integral will be in terms of y, and on the right-hand side, your integral will be in terms of x. And then once you've integrated, then you'll just solve algebraically for y, and you'll have a solution to the differential equation. One important thing about solving a differential equation in this way is when you do this antiderivative, you have to remember to write plus c, right? This constant of integration is going to turn into a parameter that parameterizes the collection of solutions. If you forget to write plus c, you'll find a solution to the differential equation, but you won't find all solutions to the differential equation.